Suppose there is a conducting wire sliding with speed v along a U-shaped conducting rail. Assume that the rail cannot move, and that the wire and the rail together form a closed conducting loop. If there is a magnetic field B perpendicular to the plane of the circuit, then charges in the bar will be pushed to its ends and flow around the closed conducting loop as an induced current. This current is given as the ratio of the motional EMF to the resistance in the conducting loop. And we learned previously that the motional EMF is equal to the product of the bar's velocity, its length, and the magnitude of the magnetic field. Let's use this result to do an example. A flashlight bulb rated at 3.0 volts at 1.5 watts is connected to a rectangular circuit of wires of negligible resistance. The circuit is placed in a uniform perpendicular magnetic field of strength 0.10 Tesla. The right wire of the circuit, which is 10 centimeters long, is free to slide and is pulled at constant speed v through the magnetic field. What speed must the wire have to light the bulb to full brightness? What force is needed to keep the wire moving? So let's sketch this scenario. We have a circuit. This circuit has a light bulb in it. This light bulb is rated to be 1.5 watts when a potential difference across its ends is equal to 3.0 volts. Now, currently this light bulb can't light, but we have a wire that is free to slide along the rails that connect the light bulb. This wire can slide with a speed v. This speed v is what we are trying to find for our problem. This light bulb will be unable to light unless there is a current flowing through it. Right now, there is no current. There is no potential difference because we haven't indicated our magnetic field. So let's go ahead and add our magnetic field to this sketch. We are told that this magnetic field is a uniform magnetic field that is perpendicular to the plane of this circuit. So we are depicting that this magnetic field is pointing away from us. And the magnitude of the magnetic field is given as 0.10 Tesla. Another bit of information that we're given is that the length of the wire that connects the two rails attached to our light bulb is 10 centimeters in length. So now that this wire on the rails can move, we know that motional EMF will establish a potential difference between the top of this moving wire and the bottom of this moving wire. Based off of what we've learned before, we know that this potential difference will cause positive charges to accumulate at the top of this wire and negative charges to accumulate at the bottom of this wire. And this is based off of the direction of the magnetic force given by the right-hand rule on the positive charges. Once we find the direction of this magnetic force, we flip our thumb, and the direction of the magnetic force on the negative charges is opposite to that of the positive charges. And that creates a induced electric field along the length of this wire. And that induced electric field establishes a potential difference. And once that potential difference is established, these charges are then free to move around in the circuit as a current. Once that current is produced, that will allow the light bulb to light. So we need to figure out how fast that moving wire needs to move in order to allow the light bulb to light to full brightness. From work we've done in previous examples, we know that the potential difference between the ends of this movable wire will be what we call the motional EMF, and that motional EMF is the product of that wire's speed, its length, and the magnitude of the magnetic field. Now, if we call the bottom part of this wire point A, and if we call the top part of the wire point B, that motional EMF is the potential difference from A to B. So our motional EMF is equal to the voltage at which the light bulb needs to have in order to reach maximum brightness. Remember, motional EMF is just the product of the wire's speed, its length, and the magnitude of the magnetic field through which it's moving. And we're saying that this is equal to the potential difference that the bulb needs for maximum brightness. So the speed at which the bulb needs to move is equal to the potential difference across the bulb over the product of the wire's length and the magnetic field. The potential difference is 3.0 volts. The length of the wire is 10 centimeters. And the magnetic field has a magnitude of 0.1 Tesla. After doing my unit check and plugging into my calculator, I get that the speed that the bulb needs to move is 300 meters per second.